Okay, I guess we're ready to start Chapter 5. So Section 5.1, these are going to be linear models, so we're going to be modeling some applications using linear differential equations, and we're going to start with initial value problems. This is going to be a fairly long section, and so I'm going to divide this up into several parts. So I think the first thing, well, first of all, the main application that we're going to be dealing with in this section involves the following setup here. So we have a spring that we're suspending from a ceiling, and we're going to attach some weight to it, so some mass m, right? And then we're going to, disturb the mass in some way. We'll pull it down and release it and so forth, and evaluate its subsequent motion. So when you, so when you attach a mass, of course, it stretches the spring a little bit, but we're going to consider this position here the initial position, right? So this distance would be the stretched distance, but that's going to be 0. This will be, or x equals 0. This will be our x equals 0. This will be our equilibrium position. Right? And the convention here is that if we pull the mass downward, if we stretch it by some distance, let's call it x, we bring the mass down here, so we're going to call that distance x, and that's going to be positive, right? So if we push the mass upward, up here, let's say, then this will be negative. So our convention, at least for the time being, is that downward is positive and upward is negative. So I know that seems a little backwards, but in this problem it kind of makes sense, because we want to measure the displacement. We want to consider a positive stretch, or stretching the string to be positive, and compression being negative. So that's the first thing we should mention here. Right, so we're using x instead of y. So again, another issue is that, right, the displacement will be x as a function of time, even though this is vertical, so you might be tempted to use y. We're using x. And in fact, it really doesn't matter if you just, right, have a wall here and you attach a spring horizontally to a mass. As long as it slides without friction, this goes back and forth. So again, this would be positive x, and then compression would be negative x. So you can think of it horizontally or vertically. Most of the problems in this section are going to be vertically. Okay. Okay, so another thing we should also talk about before going on any further are units, because this book uses two different sets of units. One set is going to be the standard SI units. So we're talking about we've been talking about mass here, but we also want to talk about the weight of the object, right? So mass m, and then weight w. And I'm assuming most of you by now know the difference and know the relationship between these, that to get the weight, you just take the mass times g, the acceleration due to gravity. Okay, so in SI units, g is approximately 9.8 meters per second squared. So if your mass is in kilograms, right, let's say we have 1 kilogram mass, then the weight will be about 9.8 newtons. Okay. So if you have a 2 kilogram mass, then the weight would be, what, 19.6 newtons, right? Right. So in our British units, or American units, you have g is 32 feet per second squared. And so you're used to weight being in pounds. That's not a big deal. But mass, it's in this really weird unit called a slug. which I only vaguely remember from a long time ago. This is not really used that often, but yep, so a mass of one slug weighs 32 pounds, again, approximately. Okay, so that's just to get the units out of the way here, right? So when dealing with springs, we use Hooke's law, which relates the force needed to either stretch or compress the spring is just equal to k, some constant k, times the displacement x. Okay, so this is Hooke's law. So think about what k is. K is just going to be the force divided by the displacement. So the units, this has units of either newtons per meter or pounds per foot. Again, depending on which unit you want to use here, right? So, and it's just a constant, right? At least we're assuming it's a constant. And for most problems we're going to deal with, it will be just a constant, right? And again, within a reasonable frame here, if you don't stretch the spring too much or compress it too much, or, you know, this law will apply, you know, in our special cases here, right? Okay, so with that out of the way, now we can talk about the first topic here, which is actually, section 5.1.1. This is free undamped motion. So free refers to the fact that we're not applying any external force. Well, we might be initially, like if we might have to pull it down or push it to compress it, but once we let it go, it's free motion, right? Undamped refers to the fact that there's no air resistance, there's no friction, right? So we're at least pretending that this is taking place in a vacuum, and there's no medium through which it travels. So that's undamped, right? Yep. So for free undamped motion, we just essentially take Newton's second law here, mass times acceleration, and set that equal to the force required to, or the force using Hooke's law, which is equal to k times x, right? And a, of course, is just the second derivative of displacement. Oh, I keep forgetting there should be a negative sign here because if you pull it down, the force is acting upward. So these should be negative here. And in fact, you can add the kx to both sides. So you get m times x double prime plus kx equals 0, which is a standard homogeneous second order differential equation. And typically, to put it in the normal form, we're going to divide everything by m here. Right. And so then we get x double prime plus k over m. And I'm going to give this a slightly different name here. So instead of k over m, we're going to use the Greek letter omega. In fact, we're going to square it for reasons that will become apparent soon. So this is x double prime plus omega squared times x equals 0. Okay, so omega squared, or omega itself is an angular frequency, and so it just has units of, you know, radians per second, right? Yep. So omega itself, of course, is just the square root of k over m. Okay, so how do we solve this? We've done it probably many times already. We look at the auxiliary equation. So that's just going to be m squared. Oh, yes, m, not the same m as this, right? So yeah, this is why I think I said long time ago that I don't like m when using for the auxiliary equation. So I'm going to use r. So r squared plus omega squared equals 0. And the solutions to this is going to be plus or minus I times omega. And that's one reason for having omega squared here, is that we don't want to take the square root of omega here, right? So this works out pretty well. And because these are imaginary numbers for the solution, I think I can squeeze that in here, we're just going to get C1 times cosine of omega t plus C2 times sine of omega t. And so that's the general solution to the to this equation here. Right. So no surprise in the sense that if you pull a swing and let it go, maybe I'll do that over here. Typically, it's just going to bounce back and forth, right? So you're going to get a sine or cosine function, right? Or some linear combination of sine and cosine. So yeah, no surprise here that you get sines or cosine functions, right? This just oscillates back and forth in a periodic function. So that's how that goes. So I'm going to sort of rewrite this in a slightly different way here. Actually, before we do that, okay, so there's another way to write this equation here. So we can write x of t as a times the cosine of omega t, and then minus some other angle phi, right? And these are completely equivalent. It's just a different way to write it. You can go through the algebra here, and what you'll get is that A is related to the C1 and C2. It's actually just the square root of C1 squared plus C2 squared. Right? And then this angle phi, so we call this angle, this phi here, we call this the phase angle. Right? So it's like a phase shift. Right? And phi is really just the arctangent of C2 over C1. Well, so maybe I'll write it as the tangent of phi is C2 divided by C1. So you just have to be careful when defining it this way. Oops. C2 over C1. Just make sure you know which C1 and C2 is negative or positive, and then make sure you're in the right quadrant. Yep, so that's the relationship between the C's and the A and the phi here, right? So you probably remember why we call it A. A is for amplitude, right? So the A is also the amplitude here. Although it could be positive or negative, right? So the amplitude is really the absolute value of A. We're going to consider amplitude to be a positive number, right? Also, another property of when you go back and forth like this is how quickly you go back and forth, right? Do you have something that oscillates much faster, that has a higher frequency, and a smaller period, right? So let's define frequency. I'll just use f, although be careful, not f as a function, but f as just a letter. For frequency, it's going to be omega divided by 2 pi. Remember, omega is the angular frequency. So to get just the frequency, you have to divide by 2 pi, right? 2 pi radians per cycle, in other words. So that's the frequency. And it's inversely related to the period. The period is just how long it takes in seconds to go back and forth, right? So this would be one complete period. And so we use the letter T for period, and that's defined to be just either 1 over the frequency or 2 pi divided by omega. Okay. So, yep, so that's frequency and period. Okay, so now I think we can do our first example. So example 1. And again, I'm going to pull this from the book. I think this is number 8. So 5.1, number 8. Oops. Right. And there's several parts to this, although I'm not sure I'm going to do all the parts. Well, I don't know. Let's see. So we have actually, hang on a second. Let me get the problem. Okay. So magically, the problem appears from the book here. So this is we have a mass weighing 32 pounds, stretches a spring 2 feet. We want to determine the amplitude and period of motion if the mass is initially released from a point that's 1 foot above the equilibrium position with an upward velocity of 2 feet per second. So I might quibble with the word released. Then we're not really releasing it. Releasing it just means, let it go. We're actually going to be sort of giving it a push with an upward velocity of 2 feet per second. So we're initially pushing it from a point 1 foot above equilibrium position, and we're pushing it with an upward velocity of 2 feet per second. Right? And then the second question is, how many complete cycles will the mass have completed at the end of 4 pi seconds? Okay, so let's see. What do we know? Well, we know from Hooke's law that F is equal to K times X, and F is the force, that's the 32 pounds. So they didn't even mention that the mass here is 1 slug. But you'll see in other problems they mention slugs for mass. You just again multiply by 32 to get the weight. And so this is going to equal K times 2 feet, which means K is just going to be 32 divided by 2 pounds per foot, or 16 pounds per foot. Okay, so that's K. That's the spring constant. Right? K is essentially a measure of how stiff the spring is. So the bigger the K, the bigger the K, the more force you need to move at a specific distance. Right? So X being the displacement or distance that you're stretching it or compressing it. Okay. Right. So we know what K is, and in fact, right away we can get. Oh well, actually, before we get that, what's the mass going to be? Right. Remember, 32 pounds is a mass of, one slug. So that's m. M is just 1. Right. But if we know K and we know M, we know omega. Oops, that's up here, right? Omega is just the square root of K over M. So omega is the square root of K over M. K we just calculated is 16, M is 1. So the square root of 16 is 4. So this is 4 radians per second. Okay. And so from that we can calculate the period, because they do ask for the period of motion. So the period, T, is just 2 pi divided by omega. So that's going to be 2 pi divided by 4, or pi over 2. And this is just in seconds. Right? So roughly 1.57 seconds, if I remember right. So just over 1.5 seconds to go back and forth, right? So that's one period. Yeah, and the frequency would just be the reciprocal of this, right? It's going to be 2 over pi, 1 over seconds, or 2 over pi hertz. they didn't ask that, but let's mention it. So frequency, that's a Q, is just 1 over the period. So this would be 2 over pi. The units are hertz, which is the reciprocal of seconds, right? Inverse seconds. All right, what else do they want? Oh, they want the amplitude, right? So they want this, they want A here. So, well, we could do this as finding C1 and C2. Yeah, I'm just wondering if we should do it that way. So again, because this is free undamped motion, we have the solution already given is here. And in fact, we know that omega is 4. So x of t is just going to be C1 times cosine of 4t plus C2 times sine of 4t. Okay. So how do we find C1 and C2? Well, that's based on the initial conditions, and they give us these initial conditions here. So the initial displacement is 1 foot above equilibrium position. So remember, if you're going above, that's going to be negative. That's a negative displacement. So x of 0 is really just negative 1 foot. Okay. And we're giving it an initial upward velocity. So that's the derivative, x prime, for the velocity. And it's going to be an upward velocity. So again, upward is negative. So negative 2 feet per second. Okay. Yeah, so maybe I should include units here. Feet per second, right? And so, yep, using these, we can quickly figure out C1 and C2. Yep. So x of 0 is just going to be C1, right? Because cosine of 0 is 1, sine of 0 is 0. So we know C1 is just negative 1. Before we plug in 0 here, maybe we should take the derivative of this. The derivative is just going to be negative 4 C1 sine, I almost wrote cosine, sine of 4t plus 4 times C2 times cosine of 4t, right? Oh, and we already know that C1 is negative 1, so this will be positive 4 times sine of 4t plus 4C2 cosine of 4t. Now we can plug in 0 for t here, right? So that's just going to be 0 plus 4 times C2 times the cosine of 0, which is 1. And remember, that was equal to negative 2, so that tells me that C2 is just going to be negative 2 over 4, or negative 1/2. And so now well, if I can erase, I would, but let me write down the equation of motion here. So the displacement x is just going to be negative cosine of 4t, and then minus 1/2 sine of 4t. Right. So this describes the displacement as a function of time. And if you want the velocity as a function of time, remember that's just the derivative. So that'll be, let's see, negative, so that'll be positive 4 sine of 4t, and then minus 2 cosine of 4t. 4 times t, not 40. Okay. All right. So now what? Oh, the amplitude. We were trying to get the amplitude, right? Well, remember, amplitude is just the square root of, let me write that down. Amplitude A is just the square root of C1 squared plus C2 squared. And so that's just going to be the square root of negative 1 squared plus negative 1/2 squared. So that's the square root of 1 plus 1/4, 5 over 4. So the amplitude is the square root of 5 over 2. Sorry, that's a 5. And yeah, it's positive, right? Remember, amplitude you take the absolute value, so it should be positive. And so I guess that answers that question. This is the amplitude. Let me see if I can fix that a little bit, make it look a little bit neater here. Square root of 5 over 2. So that's the amplitude. Okay. And the units are feet here. Sorry. Yep, this is in feet. Yes. Okay. All right, so that, I think, takes care of the first problem. The second problem is how many complete cycles will the mass have completed at the end of 4 pi seconds? So let's think about this, right? If one period, right, is pi over 2 seconds, right, how many periods, how many complete cycles or complete periods will be completed after 4 pi seconds? So scroll down a little bit here, and let's see if we can figure this out. So the number of periods, let's just call it n. So this is the number of periods or cycles, right? So the number of periods times each period has to be 4 pi seconds. So n, the number of periods, is just 4 pi divided by t, which is just 4 pi divided by pi over 2, which should be 8. Right? The pi's cancel. 4 times 2 is 8. So, yeah, so I think we get 8 complete cycles or 8 periods in 4 pi seconds. And I think that answers all the questions we have here. So I hope this helps. This is a fairly typical example in dealing with free undamped motion, right? So we're assuming that this is just going to go back and forth forever, right? With the same amplitude, same period, forever. And again, this describes the, right? So if they ask for x, in other words, to solve the differential equation here, differential equation being this way up here, right, for free undamped motion, you always get this as a solution, and I just filled in the initial conditions to get the C1 and C2. Okay, so I hope that helps.